In class, we're taking a look at this problem involving a eraser that is sitting on a turntable or record player. And we just wanted to explore different ways we could calculate some rotational problem or circular motion problems with this and relate it back to other things we know like friction. So for part A, what is the angular speed in radians per second? And we're given at a rotational rate in 33 1/3 RPM. So this is just a conversion problem where we do 33.333, or some people are putting it as 100/3. If we've got that as revolutions per minute, we just go through some conversion tables here. We can say that 1 minute is equal to 60 seconds, so the minutes cancel. Then we can continue that table and say that 1 revolution is going to be equal to 2 pi radians. And we can do the conversion, and let's see what we get here. I've already got the answer right there. We get 3.49. So 3.49 radians per second. Just a little exercise there with conversion. For part B here, we want to know what the tangential speed is, and tangential speed is going to be omega times r. So we're going to take that omega that we just converted to get, 3.49, and we're going to multiply it by the radius, which in this case 10 centimeters or 0.1 meters. And we get 0.349. Last step, finding the centripetal force. Fc would be m times v squared over r. Sorry, vt for tangential velocity. And we got all these numbers, so this is pretty straightforward. And if we do that, we get a teensy tiny little number of, you guessed it, 0.12. I'm sorry, 0.012 newtons, so very small amount of force. So we'd already kind of done that, but now we get to the good one. Part A of the challenge question. What will happen to the centripetal force, I'm sorry, in this case, just centripetal acceleration, if we move the same eraser to a position of 0.2 meters from the center of the circle? And a lot of people will think, okay, centripetal acceleration, that's going to be tangential velocity squared over radius. So if I increase the radius, I should, my denominator gets bigger, then AC should get smaller. But you got to remember, tangential velocity is also dependent upon the radius. So if the radius goes up, tangential velocity goes up as well. And how does that factor in to our centripetal acceleration equation? If both the tangential velocity and the radius are going up, whichever one of them maybe is more of a factor in the equation is going to cause the biggest change. In this case, because the tangential velocity is proportional to the radius by that factor of r, if it were to double, then you're going to get a factor of doubling in the denominator, and then you're going to get a double squared in the numerator, so the centripetal acceleration will actually go up. Now, we hinted at in class that there was a different way of writing centripetal acceleration. If I take that v squared over r, and I substitute in the omega times r and square it, I'll have omega squared times r squared over r, or omega squared times r. And I think if you're looking at the equation this way, it's a lot easier and quicker to see that if the radius increases and omega is going to stay the same, the record player is not turning any faster in terms of an angular speed. If the radius gets bigger, then the centripetal acceleration has to go up as well. That's a tricky one. Now, part B of this question is asking to do some calculations. It says if the coefficient of static friction between the eraser and the turntable is 0.5, and the radius value is going to be 0.2 meters, we want to find the maximum rotational rate that the record can be at before it slips. So we're going to have to call in here the idea of net force producing mass times acceleration. We're going to have to include friction, and we're going to also have to include the idea that omega can be the rotational rate multiplied by 2 pi. So there's going to be a lot of little equations we're going to have to work out here. But first off, let's approach it from that idea that a net force is going to be, in this case, in the radial direction. If we got the record player and we got the little eraser on it, there's going to be a force towards the center of the circle, and that force is being provided by friction. So the only force along the radius is the force of friction, nothing working against it, and that has to be equal to m times a, but because it's centripetal, it's center pointing, it's going to be a sub c. So we can put in the formula for friction on a horizontal surface, mu times mg equals m times v squared over r. The masses cancel out, so we don't really need them. And we know what the mu is, we know g, we've got the radius, so we can get Vt, and then we can get omega, and then we can get the RPMs. A hard time writing here. It's not a one-step process, of course, but we can do all these steps together. So let's go ahead and solve for V sub t. If I multiply the r over and square root, I'll have mu times g times r, which in our problem will be 0.5 times 9.8 times 0.2. Let's see what we get there. Do a little calculation here. I get 0.99, 0.9899. Let's just call it 0.99. And that's going to be meters per second. And I can get back to omega then by using the equation we had up above, right here. And we can solve for omega and say that omega is going to be Vt over r. So 0.99 divided by 0.2. And I get, excuse me, 4.95. Of course, I'm doing a little bit of rounding here and there. And once I get that, I can convert that from radians per second to rotations per second by dividing by 2 pi. Rotational rate. So 4.95 divided by parentheses 2 pi. Gotta remember those parentheses. And I'll get a 0.788, and that's going to be rotations or revolutions per second. And now I can go ahead and convert and say I'm going to multiply that by 60 seconds for every 1 minute, and I get about 47. So 47 RPM. So that's a little bit faster than a 45 RPM record, but it's significantly faster than the 33 1/3 that we were at originally. So I think the eraser's not going crazy unless we start cranking up some old 78 records. But that's it for this problem. Hopefully you find that helpful.